Hi everyone. In this video, we are going to talk about non-backtracking random walks and the surprising relation to Chebyshev polynomials. This is actually a standalone video. I mean, we are going to use it for analyzing our LPS construction as part of our seminar. But generally, if you're interested in non-backtracking random walks and this relation to Chebyshev polynomials and trigonometric identities and so forth, then that might be useful. Right. So non-backtracking and random walks. So let's start actually by setting some notation and recalling, how in operators form you encode standard, possibly backtracking random walks. So let's say you have some undirected, for our particular case, a graph G on n vertices. The adjacency matrix of G, denoted as A here, is the matrix whose rows and columns are indexed by V, the vertex set. And at entry UV, you put 1 or 0, depending or not whether there's an edge between U and V. If there are multiple edges, actually, it is useful to put the number of edges here. In fact, even if you start with a graph which is simple, namely, in particular, it has only ones here, no parallel edges, you can easily, and you will see here, you can easily get into a situation where you have multiple edges. So it is actually useful to consider here as actually the number of edges between U and V, okay? Yeah, and the nice thing about this matrix, this operator, is that its half power encodes length R random walks, length R walks or paths between U and V. And I say between because the graph is undirected, so it's symmetric. Right, because if you think about it, A to the R at entry UV is precisely the number of paths of length R from U to V. And also here you can see that you will have parallel edges here because there could be many paths of length R from U to V, and these will contribute, each of them will contribute an edge in this kind of power graph. Okay. Anyhow, so what I'm trying to say is that standard walks on a graph are easily expressed using operator form. Like you just take the adjacency matrix, take it to the power R. And we are interested in what's called non-backtracking random walks. So what is a non-backtracking random walk? I always keep saying random because I'm used to it. So a non-backtracking walk, well, a path of vertices V0, V1 up to VR is called non-backtracking. So it's possible it's a path if each of these is an edge. But importantly, you don't want to immediately regret what you just did. You don't want the VI minus 1 to equal VI plus 1. So you don't want to go, and then immediately afterwards go back. Regretting immediately, in which case, this is VI minus 1 and VI plus 1 at the same time. You are allowed to go back to the same vertex, like that maybe, or even in a shorter path, but not immediately returning back, okay? So you'll see the importance of that. It gives you the better kind of behavior and gives you the precise bounds that we want. But generally, that's what you want to understand, a non-backtracking random walk. And, you potentially, for every given number R, not potentially, you can just do it. You can form the matrix which we are going to denote by R, A sub R, rather than A to the power R, that encodes how many non-backtracking walks you have between U and V. This is symmetric because the graph is undirected. So you can form this matrix AR by just, putting at entry UV the number of non-backtracking paths between U and V. Okay. And the question we want to ask ourselves is what's the relation between this and A, like the basic matrix that encodes the graph. So let's see. So for a k-regular graph, let's consider only k-regular graphs for simplicity. Well, obviously A0 is identity. I'm kind of assuming there are no self-loops. I'm not sure it's required here, but A0 means, you're looking at all empty paths, and between every vertex and itself, there is one empty path. If there is a self-loops, maybe there are a couple. So let's assume there are no self-loops. And between two distinct vertices, there are no paths at all, backtracking or not. So A0 is I, which is the same also as A to the power 0, because there is no difference between backtracking and non-backtracking if you have only one or 0 steps. Similarly, there is no difference between non-backtracking and backtracking walks if you have only one step. So A1 is A, which is also A to the 1. The first time you see a difference is when you look at length 2 non-backtracking walks. And if you think about it for a second, you can express A2 as A squared minus K times I. Right, and the reason is that, this matrix includes all length 2 walks, namely at entry UV, you have how many walks of length 2 you have between U and V, but some of them are backtracking and you want to remove them from this counting, right? Kind of, but not exactly like inclusion-exclusion. So, in length 2 walks, what can go wrong? Like, what kind of backtracking walks do you have that you want to omit? Well, they have to come from a vertex to itself, because if you start at U and you go somewhere, you go to V, then the only time you are getting the chance to backtrack is, going back to U because that's your last step. And so definitely we're going to only subtract paths from a vertex to itself. That's why you have this I here. So I'm only kind of correcting the entries on the diagonal, because outside of that, there are no issues. And how many of those do you have? Well, exactly the degree, which is K, because you start from U, you have K options, of where to go, the degree of the vertex. And for every such option, you have a backtracking walk that you want to reduce. So that explains why A2 is A squared minus K times I. So note that at least in these simple cases, kind of interestingly maybe, you can express A0, A1, and A2 as a polynomial in A. Right, in backtracking walks, this is the simple polynomial A to the power R. Here you see that it's kind of more interesting. I don't know, it has minuses and it encodes also the degrees and so forth, but potentially it could break here. Luckily, it doesn't. So, you can ask, is there a polynomial such that AR, the non-backtracking length R walks of G, is there a polynomial that depends on R, of course, such that AR can be expressed as the polynomial evaluated at A? So, for example, this is the polynomial 1, this is the polynomial x, and this is the polynomial x squared minus k. Yeah, it turns out there is one, and it is surprising to me at least, but it's very simple to see. So let's see that. So this lemma tells us that, first of all, and that's already kind of interesting, and essentially implies the fact that there exists a polynomial more or less, is that A and AR commutes. Okay, it's going to be a corollary of what we're going to do, but A and AR commutes. Well, maybe it's not that surprising, I don't know. I mean, there is some symmetry between backtracking at the beginning or at the end or something, but that's a fact that we're going to prove. And moreover, there is a recursive relation between AR plus 1, and AR minus 1. So it turns out that we're only going to prove this one, but the same one holds for the other, for this thing. So we're going to prove that AR time A is AR plus 1. That's kind of the leading term in the recursion, plus K minus 1 times AR minus 1. Okay, and that immediately gives you a way of computing larger A of larger R's in respect to like two previous ones. So let's see why this is true. And then we are going to derive from that the polynomial that we care about. So let's look at this expression. That's why I wrote it like that, AR times A. So what's going on here? So at entry UV, what you're doing is you're doing a non-backtracking walk from U to some vertex W of length R, and then you take a step. That's the A, right? Um, hmm. I think I'm actually doing this thing, because I'm multiplying from the right in my notation, but never mind. Yeah, don't worry about that. So let's split these two options. I mean, again, we are taking a length R non-backtracking walk starting from U ending at W, and then we are taking one step, backtracking or not. So let's split these paths according to whether or not actually the last step did backtrack. Okay. So you start from U, you go to W, non-backtrackingly, and then let's consider the first case in which V doesn't backtrack, so it doesn't go back to this previous vertex you visited at. So this means, I mean, all of these paths in which the last step, doesn't backtrack, actually gives you a path that non-backtracks of length R plus 1, and all of them are formed like that. So these paths, this subset of the paths that we count here is precisely captured by R plus 1. Like the UV entry of R plus 1 captures what we just said. Now, in the other case, where you know that the last step backtracked, then this means that the picture looks like this. You start at U, after R minus 1 step in which you didn't backtrack, you go to a vertex, the vertex V, and then you do one more non-backtracking step because you're still in the first R steps which non-backtrack. So you go somewhere that is not this previous neighbor of V. It's one of the other K minus 1 neighbors of V. So I denote him by W1 up to WK minus 1. Right, so that's your first R steps. You didn't backtrack. And then you have to backtrack. So you go back, like from wherever you are, you just kind of deterministically go back to V because you need to end at V. So that gives you, I mean, the way we broke it here, you have AR minus 1, length AR minus 1 path. And then you have K minus 1 options of which vertex, which is a neighbor of V to visit, which is not this one because you don't want to backtrack. And then there's like a deterministic step going backwards to V. So this captures, this number at entry UV captures all of this type of walks that are captured here, which do backtrack. So altogether, we get this result. Right? And similar, I can do it for A and AR, it's the same thing. Yeah, so I just wrote it here, see, and just remind ourselves of that. And let's look how it looks for example, for R equals 3. We did already 1 and 2 and 0. So what about A3? So just plugging into this recursion, R equals 2, and getting by that A3, you see that A3 is, so A3 is A2 times A minus this thing, minus K minus 1 times A1, which is A. Now A2, we already did, is A squared minus Ki. So plugging it here, you get A cubed minus 2K minus 1A. And you can think for a second, I mean, maybe, I mean, you can reason about it like as a special case of what you did before, but you can also think about it as is. If I would have given you just A3 like that, why is it the case? Right, so let's just try to count it without the recursion, like more directly. So let's consider a path which starts at U and ends at a neighbor V and backtracks. Then we're also going to explain why you can only backtrack on these pair of vertices which are connected by an edge. But if you start at U and then you visit some vertex, so let's assume, let's go for this case, we'll visit a vertex, the vertex V that you're considering now. So I have like one option here. And then, I mean, you do need to backtrack and return to V. So now from V, you can actually choose any of its neighbors, including U. You have K options, and you will go there. Let's say it's here, and then you're going to go back. So you're backtracking at kind of the last step. So these give you K options. In the second case, the first step is not V, so it's some it's some W. So this is U, this is W, because we already considered all backtracking walks from U to V, which visit V immediately after visiting U. So you look at U and then you look at W. You have K minus 1 options for that. And now you need two things. You have two steps and you need to end up at V and backtrack. So you can't just go to V now, because then if you'll backtrack, you will go away from V. So you have to go back to U so that you can backtrack. So here you have K minus 1 options. Here you have one deterministic option. And then you have one last step. This is the second step. I mean, I'm writing steps. You have one last step, the first step, at one option to go to V. So all in all, you have like K options from that case and K minus 1 options from that case. So this is the 2K minus 1. And that's for every two vertices U and V that are connected by an edge. So that's why you have this 2K minus 1 per edge, like at every entry of A. So if you think about it, if U and V are not connected by an edge, their distance is at least 2, then there's no way you're going to backtrack. Because if the distance is 3 or more, then you need 3 steps just to get from U to V. And that won't allow you enough time to backtrack. And if the distance is 2, then there is a parity issue, because you need to do 2 steps and backtrack and do one more step at least. So that's 4 steps. Anyhow, try to convince yourself in a more accurate or slightly more formal way. But anyhow, I hope this helps. It turns out that A3 is this relation. It only gets nicer. So A4, unless I made a mistake in the calculation here, it's something like that. Okay, it's like you take all length 4 paths, but then you correct by subtracting all of those paths of length 2 that you have in the graph, weighted appropriately, and then kind of correct back things that you overcorrected when the start and end in vertices are the same. It's actually nice to do it by hand one time to see that you get it, but anyhow. Yeah, so that's that. And once you have a recurrence relation, you do want to form the generating series for that and hope that this generating series, the power expansion, will be insightful. I mean, maybe it will have a compact form, or it will shed light on maybe there is another series that has nothing to do with your series, that has the same compact form of its generating series and so forth. And that's going to be the case here. So if you think about this relation and you're trying to encode it as a power series, then what I'm claiming is that this identity holds. Right, so what's written here? So on the one side, you have the power series that I care about, the generating function. The generating function. It's better to say that. And what I'm claiming is that if you multiply it by this expression, you get this expression. So let's see why that is. So let's just compare coefficients. So the coefficient of t to the 0 here, it's I. Right, the coefficients are matrices. Okay, so the coefficient of t to the 0 here, it's I. And here, t to the 0 is contributed. It gives you like A0, t to the 0 from here. And here you have t and t squared. So the only way to get no t's, or coefficient of t to the 0, is taking this I. And A0 is I, as we said. So the coefficient of t to the 0 is the same. Now the coefficient of t, here on the right-hand side, it's 0. You have no t's here. And on the left-hand side, well, you do have like t's, but they cancel out because you have A0 plus A1t plus stuff we don't care about, because I'm caring about the t coefficient. And then here you have I minus AT plus thing I don't care about. I mean, one thing, it's the t squared coefficient. And if you look at it for a second, you get, so this is I, and this is A. Right, so you have like I minus AT times I plus AT, which is I minus A squared, t squared, no t's. Right, so this is I minus A squared, t squared. I mean, potentially there are other t contributions, but anyhow, there are no t squared contributions, but there are no t contributions anymore. So indeed, the coefficient of t on both sides is equal to 0. The coefficient of t squared here, it's minus I, and the coefficient of t squared here, okay, so let's write it again. So it's a0 plus a1t plus a2t squared. I don't care about the rest, times I minus at plus k minus 1 t squared I. Maybe I'll just this here for a second. And okay, so that's actually slightly more annoying. So that's I plus at, because a0 is I and a1 is t. Now a2, remember, is a squared minus ki, if you remember. That's from here. Right? You take all length paths, but you backtrack those that you immediately go back and forth. You have k options for every vertex. And here you have I minus at plus k minus 1 t squared I. So the coefficient of t squared will, okay, so you have this I and this thing. So that's k minus 1 t squared. No, there's an a squared there. Oh, sorry. Yeah, that's fine. I'm looking at the coefficient of t squared, not a squared. So the coefficient of t squared is I times this, which is, so let's remove that. The coefficient of t squared from this is k minus 1I. And then I'm looking at this and that. So that will give you minus a squared. Okay, times t squared, but I'm looking at the coefficient. And then this times that is plus a squared minus ki. So if you look at it, the a squared cancels, and you have k minus 1I, and you subtract ki. So you are left with 1 minus I, which is precisely the coefficient of t squared here. So that's actually, these are actually the base cases in a sense, because the depth of the recursion, you need to go 2 back. I mean, well, the last one was maybe a little bit redundant, but anyhow, generally, if you think about it for a second, what happens to a higher t, then the coefficient here is going to be 0 for every t larger than 2. Here it's 0. So I'm looking at the coefficient of tk. Oh yeah, k is a bad name. Tm, where m is at least 3. So here it's 0, and here it's, well, yeah, so it's kind of annoying. I need to pick the ones that I care about. So I think I need to go back 2. So am minus 2. I mean, this is going to go most 2 to the right. So I need to go start from 2 to the left. T to the m minus 2 plus am minus 1 tm minus 1 plus am t to the m. There are things from before and things after, but I don't care about them because they won't contribute to 2 to the m when I'm going to multiply it by that. And when we are going to multiply it by that, well, who contributes 2 to the m? So when this guy meets this guy, we get a t to the m. So you get like k minus 1 am minus 2. And then when this guy meets this guy, and the order is important, so it's non-commutative, right? So it's a minus am minus 1 a, and then there is the last one, last pair, this and that, yeah? So that's plus am. Yeah, and that should equal 0. And if you look at it for a second, hopefully this is exactly that. Maybe I shifted the indexes by a 3. Right? If you take m to be r plus 3, so this will match that, then you see that no. So if you take m to be r plus 1, so that this will match that, you'll get the semi-recurrence relation. Right? The k minus 1 multiplies the thing that is 2 below you, and you have this one. Yeah, anyhow, it's kind of long and tedious to check, but this is the way to encode using generating functions the recursive relation. And now instead of writing it like that, I mean, I care about this thing, right? So instead of writing it like that, I'm going to write it this way. Namely, the generating function for the ARs for the ARs is given by this expression, right? So I just taken the inverse of that, and this is a formal inverse. I mean, it's a kind of formal symbolic inverse. You should think of it as you work in the ring of power series where the coefficients are matrices. Or if you want, you can find T's for which this has no convergence issue, but you shouldn't do that. Just a formal thing. Right, anyhow, to sum up, we have that we know the power series or the generating function in a compact form for non-backtracking random walks. Now, there's one little thing that we want to kind of juggle a little bit this right-hand side, because the 1 minus t squared is slightly annoying. So what we are going to do is to consider a slight variant of AR, which will have a nicer compact form. Right, so this is what we just proved. And let's denote by t sub m the sum when r goes from 0 to m over 2 of a m minus 2r. So you kind of count in matrix form, I mean, how many non-backtracking random walks you have up to length m in this form. So r is so you always subtract an even number of steps. Okay, and the nice thing about this, I mean, this is slightly more convoluted combinatorially, maybe, but in terms of from the analytic point of view, from the generating function point of view, it has a slightly nicer form. The 1 minus t squared just becomes 1 at the enumerator. So that's what we want to prove. It's a very simple check. Right, so this is again what we know. And let's look at the generating function of the TM sequence. Well, for every m, Tm was defined like that. So that's just the definition of Tm. Nothing happened here. And then what you do is you just switch the order of summations. So that happens here. And when you do that, you can shift t to the 2r out of the, you can kind of take it out of the first sum up to here. The reason that's nice is because now this expression inside is, the indexing is just weird, but this is precisely the generating function for the a's, because m starts from 2r and all the indices are m minus 2r and so forth. So we know that this is the expression that we had before here. In particular, it's kind of independent of r. So it goes outside of this first sum, and this first sum is also a very simple power series, right? It's a geometric series, which was kind of deliberately chosen to be like that. So that's 1 over 1 minus t squared, which cancel the 1 minus t squared that we had initially. So you get the result that I wanted. Okay. So now let's leave that aside for a second, and let's consider the following question. I mean, as I said, what's happened here is that we kind of identified the generating function in compact form of non-backtracking random walks, or rather a kind of a variant of those, the TMs, not the AMs. And this power series, I mean, this compact form of a generating function is actually well known. So from essentially Trigo, they correspond to the Chebyshev polynomials. So let me get to the same kind of miraculously get to the same compact form of the generating function for the non-backtracking random walks from for a completely different problem. So the problem is as follows. Say we want to compute or write sinus of, or express sine of m plus 1 theta, where m is an integer, 1, 2, and so forth, in terms of sine theta and cosine theta. Right, so I mean, you computed sine theta and cosine theta, and you want from that to infer sine of every multiple of theta. In particular, we would want to have, for some reason, we would want to have a formula that involves a sine theta times a polynomial in cosine theta. It's not clear that it exists, but it does exist. So that polynomial, u sub m, is actually, it's called the Chebyshev polynomial of the second kind. Don't worry about it. We're just going to call it the Chebyshev polynomial. So for example, a sine of 2 theta, it's 2 sine theta cosine theta. So you see, you can write it as sine theta times this polynomial 2x when x is applied to cosine theta. So u1 in this notation is 2x. And if you're going to do sine 3 theta, well, it's sine 2 theta plus theta, which use the sine cosine plus cosine sine thingy. So, yeah, so what did I do here? Right, so I 2 sine theta. Oh, yeah. So I used again the sine 2 theta to do a 2 sine theta cosine theta, and I multiplied it by the extra cosine theta that you have here. So that looks good. It's a sine theta times a polynomial in cosine. As for the second summand here, I used the cosine 2 theta. I opened it up as a, co minus cc, this usual thing. So you get cosine squared theta minus sine squared theta times the sine theta that sits here. Now we don't like sines, so we replace that sine squared with 1 minus cosine squared, which altogether gave us this 2 cosine squared minus 1. So, all in all, you get this is sine theta times this polynomial in cosine. Right, you have a 2 from here and a 2 from here. So that's a 4. So this means that U2 also exists. I mean, it wasn't an overkill over requirement to have this kind of form. And U2 is actually 4x squared minus 1. And generally speaking, you can just continue doing that. It's not completely trivial, but it's not so hard. And you can show that actually un plus 1 satisfies this equation, this recurrence relation. And if you think about it for a second, the generating function for that, kind of similarly to what we did for matrices, but now for functions, what you can show that the generating functions for the UMs of x is this expression, which is like, looks quite similar to what we had before for the generating function of the TMs, right? You have the 1 over, good, and then you have 1 in both cases. Here you have the coefficient of t is minus a, the coefficient of t here is minus 2x, okay? There's a difference. And here the coefficient is k minus 1, and here it's just 1. But that's just kind of because we didn't kind of normalize correctly. So what we should do, I mean, right, if you really want to get x here instead of 2x and k minus 1 here, because you want it to be resembling to that, then you can do the following transformation of coordinates or variables. Let's map x to x over 2 square root k minus 1. Note the 2 square root of k minus 1 from the Ramanujan or Alon-Bopana bound. And at the same time, change t to t times square root of k minus 1. Right, so what will happen? So x times t, which is, 2x is now becoming, okay, so let's do it carefully. So, right, so when you do that, let me start from the left-hand side. So the left-hand side becomes this thing, right? Because you change x to x over 2k minus 1. So instead of an x here, you have x over 2k minus 1. And instead of the t to the m, you have t to the m times square root of k to the m, because the new t is t times square root of k minus 1. So the left-hand side changes like that. And the right-hand side is similar to the right-hand side here. Well, at least if you're going to plug x equals a, if you are going to apply the polynomial to the matrix. And the way to see that is just a calculation. So t squared becomes k minus 1 t squared because t becomes t squared k minus 1. So the square removes the square root. And the xt becomes 2xt becomes xt because the new xt's differ by a factor of 2 from the old xt's, right? If you multiply them, then you get this factor of 2. Right, so actually it's the same thing. They count the same thing. It's kind of interesting, I think. So the corollary from that is that Tm, right, the coefficient Tm is the coefficient of t to the m, small t to the m here. It's the same as the coefficient of t to the m here, which is this thing, but when you plug a instead of x. So that's what's written here. So finally, we expressed, well, not precisely the count of non-backtracking random walks, but this kind of sum over them up to m in terms of the Chebyshev polynomials of the m Chebyshev polynomial applied to a, and kind of interestingly, the normalization which occurs here just to make sure that we get the same thing hides already the 2 square root k minus 1 magical number. Now, if you're going to take traces on both sides, by the way, this looks like a TR, but it's the trace, okay? So TR times TM. If you're going to look at the trace on both sides, well, on the one side, you get just trace of T to the M. And on the other side, right, you have this polynomial applied to the matrix. Taking traces is just like, well, the trace of a polynomial applied to the matrix is just the polynomial applied to the sum of the polynomials applied to the eigenvalues. Right? How can I show it like in a simple? So if, for example, if A has eigenvalue lambda 1 up to lambda n, then you can write it like that. You have this matrix that encodes the lambda 1 up to lambda n, and then there is a base change, the eigenvector base change, and then the trace of A is the trace of that, but the trace is cyclic, so the V goes to the right of the V transpose times this diagonal matrix. This goes away because it's identity. These are for normal matrices. And so that you get the trace of the eigenvalues. And the eigenvalues of a polynomial, the eigenvalues of a polynomial of a matrix is just the polynomial applied to the eigenvalues. Yeah, anyhow. So what I'm saying is that the trace of Tm is precisely this expression. So, well, you have this factor from before, k minus 1 to the power over 2, and then you iterate over all eigenvalues, and you apply the Chebyshev polynomial to these eigenvalues, but normalized according to 2 square root k minus 1. Okay. Now, on the other hand, if you're going to look at the trace, just from the combinatorial perspective, then if you remember, Tm was this sum. So it's just taking the sum of the traces. Traces, of course, linear. The sum of the traces. And the trace of A minus 2R, it just sums up all the non-backtracking cycles. Like, right? Because you care about, I mean, the trace of a matrix is just this sum. It's this sum. And the combinatorial meaning of that is how many length m minus 2r non-backtracking walks you have from V to V, because it comes from the trace. You start and end at the same vertex. So I'm calling it non-backtracking cycles. So on one hand, we have the trace of T to the M can be expressed kind of spectrally using the Chebyshev polynomials. And on the other hand, they give you this combinatorial information about non-backtracking walks or cycles of a given length. So if you're going to denote by f sub lv, number of paths from V to V without backtracking, then what we just proved is this equality here. We proved that, on the spectral side, you have this expression involving the Chebyshev polynomials and so forth, and apply to the spectrum. And on the right-hand side, you just sum up, it's a combinatorial side, you sum up, you go over all vertices, and for each vertex, you iterate over all numbers between 1 and all r's between 0 and n minus over 2, and you look at how many paths from V to V you have of this prescribed left, which non-backtracks. It's kind of remarkable, I think. In particular, when G is vertex transitive, you can clean it up a little bit, and G is vertex transitive when you consider Cayley graphs. So for Cayley graphs, or generally vertex transitive graphs, the left-hand side, you can write it like that, because for such graphs, there is no dependence on V. So instead of summing over V all of those, you can multiply by N, and also remove the V from the subscript. Okay, so the overall thing that I want to take from this part of the lecture is actually this equation. Right, if you're going to, well, there is a normalization here, but if you're going to count how many paths from some fixed vertex to itself, because it doesn't matter who you take, you have which non-backtrack of length n-2 are iterating over all r's between 0 and over 2. That can be expressed using the spectrum, using this Chebyshev polynomial. Okay, so that's that. In the next lecture, we are going to go back to the LPS construction and apply that to that setting. But this is kind of a standalone lecture about non-backtracking random walks and Chebyshev polynomials.